Okay, welcome back everyone. This is Mr. Dubrow with a short video for AP Physics C in electromagnetism. And in this video, I want to share a couple of tips and tricks for solving problems using Gauss's law. And then I'll show you a quick example. So first, let's talk about a couple of guidelines for using Gauss's law. These are things to keep in mind. First, anytime you're looking at the electric field inside a conductor, it's automatically equal to zero. And so the question to think about is, well, why does this happen? So if you think of a spherical metal object, so it's a conductor, and if you put, let's say we put positive charges on the outside, and if you want to look at the electric field at some point P inside, well, basically what's going to happen is that in order to have a non-zero field at point P, the field lines are going to cross, and that's a big no-no. So if we look at the field from this particular charge, it's going to be going this way. And if we look at the field from this particular charge, it'll be going that way. But if we look at the field from this particular charge, it'll be going that way. And so pretty soon there's some cancellation going on. Another way to look at this, get rid of this, is that the field of one of these charges would be going outward radially in all directions. And the field of a nearby charge would also be going radially in all directions. And so you see that you start to have some issues right around here. We're not going to be able to have a situation where the field lines cross because a field line is supposed to tell you the net force on a positive test charge. And so if there's field lines that are crossing, well, what represents the net force? So it turns out that you can't have any situations where the field lines cross, and the long and short of this is that the field inside a conductor is zero. So that's one guideline. Another guideline to keep in mind when applying Gauss's law is we want to choose a Gaussian surface, and there's plenty of examples of this in the book. Such that the electric field is always perpendicular to a small dA, or an area element. And so if you think about why this is, it's kind of the same reason as number one. Because if I have some charges on top of a curved surface, if I have field lines that start going towards each other, well, we're going to have the same problem as before. So we want to choose a Gaussian surface so that at all points the net electric field is going to be parallel to dA. Okay. And then finally, speaking of charge distributions, if there's a distribution of charge, and that could be a constant rho, or else it could be a function. If we have a constant distribution of charge, rho equals Q over V, so this is a constant density. And this is a volumetric charge density. It's charge divided by volume. So be very careful. This is not voltage or anything like that. This is going to be volume. Okay, I can write. Okay, so if there is a constant charge density, then you just use a proportion. So if I have an insulating sphere that has a charge density rho, and I want to know the electric field at some radius r, let's say the radius of the entire thing is big R. So if I want the field such that r is less than big R, I'm going to need to find the charge that's enclosed within that dotted line. That's my Gaussian surface. And because the density is constant, that means that the charge density of the entire sphere is going to be equal to the charge density of the Gaussian surface, or the charge enclosed within it. So that means that the total charge of the sphere divided by the volume of the sphere is going to be equal to the total charge at radius little r divided by the volume at little r. And so what this typically ends up looking like is that Q at little r turns into our Q enclosed, which we're going to use in Gauss's law, and Q enclosed is basically a fraction of the total. It's going to be VR over V sphere, and because volume is 4/3 pi r cubed, the 4/3 pi is going to cancel out, and we're just going to have little r cubed over big R cubed. Okay, well that's not a big deal. The tricky thing occurs when rho is actually a function of the radius. So this is not constant. And in this case, you just have to use calculus and integrate. So for an example, let's look at problem, so chapter 22, number 65. And so what this is a charge distribution where when r is less than or equal to big R, rho of r is given by rho naught 1 minus little r over big R. And we're given rho naught is 3q over pi r cubed. And when r is greater than or equal to r, our charge distribution is going to be simply equal to 0. So one question that you might have that I kind of thought about when I first looked at this problem is, well, how can you have simultaneously that the charge distribution is equal to something right here, and it's also equal to 0? And so I'm talking about the point when r is equal to big R. So we'll look at that in a moment. But for right now, let's look at this problem. The first thing that we want to do is we want to figure out the total amount of charge enclosed within the sphere and prove that it's equal to just big Q. So part A of this problem, so show that Q of R equals big R, so Q enclosed is simply equal to Q. Okay, so we know that rho of R is equal to the total charge over the total volume if it was constant, but it's not. Instead, we have to write dq over dv. And so that means that dq is going to be equal to rho of r dv. So if we look at a small volume element, it's going to contain a certain amount of charge. So this is splitting the sphere up into very thin shells and integrating that. And we know that, well, first of all, the volume of a sphere is 4/3 pi r cubed. So for fancy, we can say that dv is going to be equal to 4 pi r squared dr, which makes sense because you've got the surface area times the thickness. So that's approximately the volume of a very thin shell. Okay, so Q total is going to be the integral of rho of r dr. Well, we have to be careful. We're going to go from 0 to big R, rho of r times 4 pi r squared dr, because really back here we want dv. Okay, So now it just becomes kind of a math problem. So we'll try to not make too many math mistakes here. So we want to do the integral from 0 to r, and rho of r, if you remember, is rho naught times 1 minus little r over big R, and then we have 4 pi little r squared dr. So just for fun, I'm going to take out a couple of constants. This is going to be basically 4 pi rho naught integral from 0 to r of r squared minus r cubed over big R dr. Alright, so that's going to be equal to 4 pi rho naught times r cubed over 3 minus r to the 4th over 4 big R, evaluated from 0 to big R. Okay, so that looks like 4 pi rho naught r cubed over 3 minus r cubed over 4. So one of my factors of r actually cancels out. Okay, so now this gets a little bit more fun. And so at this point we can just do a little bit of math, and we're going to get 4 pi rho naught times r cubed over 12, which is just going to give us it's going to give us pi rho naught r cubed over 3, but now we get to plug in the fact that rho naught is 3q over pi r cubed, and so magically this is going to give us that the total amount of charge enclosed, substitute for rho naught 3q over pi r cubed, everything's going to cancel except for q. So we did it. Okay, now for part B of this problem, we want to use Gauss's law to find the electric field when r is greater than or equal to big R. So first of all, this q right here represents the q enclosed when basically little r is greater than or equal to r. So that means that when we apply Gauss's law, so the integral of E dot dA is equal to q enclosed over epsilon naught. When we apply that, this is another reason why you want your electric field to be parallel. It just turns this into E times A. It's going to be equal to q over epsilon naught. So A is going to be 4 pi r squared of a Gaussian surface, which is going to be some sphere. So if this is our charge distribution contained within big R, and we want some value of little r which is beyond that, well, the only thing that matters for Gauss's law is the charge enclosed. So that's going to be q over epsilon naught, and we get the very not so surprising result that it looks like the electric field from a point charge. And so I think we're going to cut things off here. I just want to keep the videos to about 15 minutes, but in the next video I'll do the rest of this problem.